Hello students and welcome back to my channel. In this video, we'll be discussing questions which were asked from electric current. I have incorporated both DC as well as AC students because the videos are becoming too small to be seen. Because in alternating current they gave only two questions. The questions have been picked from JEE Mains exam 27 January 2024. So, in order to have at least 4 to 6 questions in one video, I have clubbed both AC and DC together here. Okay, students? Right. So, without wasting time, let us move to the question number 35. As you can see, the wire of length 10 cm and radius this is connected across the right gap of a meter bridge. When a resistance of this is connected to on the left gap by using a resistance box, the balance length is found to be at 60 cm from the left end. If the resistivity of the wire is this, then the value of R is. So in other words, we have to find the resistance, and of course from there we will be getting the resistivity. Okay, students. Right. Let me draw a rough diagram. So the rough diagram will be something like this. This is the left gap, right gap, and this is the meter bridge wire, and this is the galvanometer, and you have this balancing length. So you can see balancing length is 60 cm. So this has to be 40 cm this side. Right. So when a resistance of this is connected to the left gap, so 4.5 I am writing it as 9 by 2 ohm. Okay, students, and let us say the unknown resistance is X. So we can find X here. Yes. So we know these two ratio and these two ratio must be same. So from the principle of this meter bridge wire, we have X upon 40 is equal to 9 by 2 upon 60. So let us cancel 22s and 23s. So this 2 gets cancelled. So finally we get X equal to 3. So the resistance is 3 ohm. Okay, students. Now once we know the resistance, we can apply rho L by A. Okay. So from here we can find rho. Right. So here you can see that 3 is equal to rho into length. Length is given as 10 cm. So 10 centimeters to be converted into meters by dividing by 100, and cross sectional area will be pi into radius square. So pi, I'll take pi as 22 by 7 into radius square. So radius square is 7 into 10 to the power minus 8. I have substituted everything in assignment, students. Okay. Then, so here 7 gets cancelled. You can see. So therefore, we are left with this 3 into 22 is 66 is equal to rho into 10 to the power minus 7. Sorry, goes up, becomes plus 7. Okay, this 10 to the power minus 8 goes up, becomes plus 8, and this 10 gets cancelled. So finally we have rho is equal to 66 into 10 to the power minus 7 ohm meter, of course SI meter. So you have correct answer as 66. R is 66. Then moving to the next question. A wire of resistance R and length L is cut into 5 equal parts. If these parts are joined in parallel, then effective resistance will be. This is very simple question, student. Suppose you have a long wire, resistance is R. You cut this into 5 equal parts. So then resistance of each part will be R by 5, because as you know resistance is equal to rho L by A. So therefore I can write resistance is proportional to length. So when you divide the length into 5 equal parts, then what will happen? The resistance will also become 1/5. So each of them will be having 1/5. Now you arrange all of them in parallel. So when you arrange all of them in parallel, then you know that the resultant will be any one of them divided by the number of resistors. Number of resistors is 5. So finally we have R by 25 ohm. Option 1. Moving on to the next question. Wheatstone bridge principle is used to measure the specific resistance S1 of A given wire having length L and radius R. The X is the resistance. If X is the resistance of the wire, then specific resistance. Yes, they have used the formula R equal to rho L by A. So from here they have found the specific resistance. This is correct. The length of the wire gets double than the value of specific resistance. Now here students, you have to understand very clearly that even though rho can be expressed in terms of R, L and A, but it doesn't mean that rho depends on R, L and A. As you know, specific resistance is a material dependent quantity. You can just open a handbook of physics and you can go through the different specific resistances of different materials: copper, iron, silver, gold, etc. So since material remains same, so it will not change. So you have to be very careful, students, otherwise unnecessarily you will end up in a wrong answer. Moving on to the next question. The primary side of a transformer is connected to 230 volt 50 Hz. Supply turns ratio of primary to secondary winding is 10:1. Load resistance connected to secondary side is 46 ohm. The power consumed in it. So suppose this is the transformer, core of the transformer. This side you have primary and this side you have secondary. Now the secondary coil has a resistance of 46 ohm. Okay, if we can find the current here, current in the secondary, then I square R will give you the power consumed. I square R. Okay, right. So here, since even if you get the voltage here, voltage across secondary, then we can use Vs squared by 46. So we can easily find voltage. Okay. So therefore you can see voltage across secondary upon voltage across primary. Primary, it is clearly given that 230 volt is applied here. Then this will be number of turns in the secondary is 1, the primary it is 10. So voltage across secondary is 23 volt. Okay students, therefore the power consumed will be voltage square upon resistance. So voltage is 23 into 23 upon 46. So 23 2s are, so half of 23 is 11.5 watt. So third option is the correct option. Moving on to the next question. 3 voltmeters all having different internal resistances are joined as shown in the figure. When some potential difference is applied across A and B, the readings are V1, V2 and V3. You have to choose the correct option. Okay students, so it's very simple. You see students, this voltage V3 is distributed between V1 and V2. So we can very clearly write V1 plus V2. The voltage between V1 and V2, V1 plus V2 will be this, which will be same as V3. So it's very simple, because both of these are connected in parallel with this. So total potential difference across this combination will be equal to the potential difference across this. So we'll go with the fourth option. Right. Moving on to section B. The series ICR circuit will L equal to this and C equal to this and R equal to this connected across an AC source. The power factor of the supply. So in order to know the power factor, we should know Z, the impedance, and before we can know impedance, we should know the what we call inductive reactance and also the capacitive reactance. Okay students, right. So let us first calculate the inductive reactance, which is omega into L. So omega is 2 pi into F, frequency is 50 Hz, L is 100 by pi. So pi gets cancelled, you have 10 to the power 4 ohm. Then let us calculate XC, capacitive reactance. Capacitive reactance is 1 by omega C. So that is 1 by 2 pi into 50, into 10 power minus 3 by pi. So 10 power minus 3 goes up, becomes 10 power plus 3 by pi. Remember students, this is milli. I forgot milli is also there. So I'm so sorry students, 10 power minus 3. So ultimately it will be 10 only 10. Right. So here Pi gets cancelled. Again you have 10 power 3 by 10 power 2, which is again 10 ohm. So you can see that inductive reactance is equal to capacitive reactance. In other words, the net reactance is 0. So the circuit is in the state of resonance. So in case of resonance, as you know, the Z will be equal to R. And you know that power factor is cos phi, which is R by Z. So R by R, which is 1. Okay. In fact, there is no phase difference between the applied EMF and the current. Both run in the same phase. So angle between them is 0. So cos 0 is 1. Okay students, we'll stop here students. That's all in this channel, in this video. Thank you so much for watching my channel.